So to summarize what we talked about in the previous videos, if you have a horizontal axis of revolution that's creating the solid that you're finding the volume for, then you always have to have a dx integral. And that means your radius, whether we're talking just little r or capital R and little r, they need to be written in terms of x. Now, if your axis of revolution is vertical, the only thing that changes is your integral should be a dy integral. And you will need to decide if your cross sections are disks or washers. If your cross section is a disk, it's a solid circle. So you can see we have the area formula pi r squared, just with the constant pi already taken out. If there is a gap between your solid of revolution and the axis of revolution, then your cross sections will look like donuts. They'll be washers. And in that case, you're going to have two radii to consider, the outer radius, capital R, and the inner radius, little r. So the steps you're going to want to follow are these. Number one, determine if you have a gap between your shaded region and the axis of revolution. If yes, use washers. If not, use disks. And then determine whether your axis of revolution is horizontal or vertical. Because if it's horizontal, you'll be integrating in terms of x, meaning you want to get y alone in your equations. If your axis is vertical, integrate in terms of y, meaning you want to get x alone so that the equation is in terms of y. In this first practice problem here, you'll notice I've already generated the graph just to cut down on the amount of time that it'll take to watch this video. And I want to make sure I understand what I'm seeing. So I look for the y equals x squared portion, which is the curved part on this graph. So that's that function. Y equals 0 is just the x-axis, so that's right here. And x equals 2 is the vertical line that you see graphed here. So I can see my shaded region, and it is bounded by these three functions. Now we're going to do three different versions of this problem. First, if we rotate around the x-axis, then if we rotate around the y-axis, and then something we haven't talked about yet, what if it's an axis that's not the x or y axis? For part A, if my x-axis is my axis of revolution, then my axis is horizontal. And if my axis is horizontal, I know I need to have a dx integral, an integral where x is the variable. The next thing I need to decide is if the x-axis is my axis of revolution, do I have any gaps? So if you go from 0 all the way to 2 along the x-axis, because we want an x integral, you'll notice my shaded region is right up against that portion of the axis. There are no gaps. So because we don't have any gaps, our cross sections will be circles, and that means we should be using the formula for cross sections that are disks. So remember, we're spinning it this way, and we're going to be creating disk cross sections like these. All right, so to find the volume, if it's disk, it's a single circle. So it's pi integral r squared dx. My limits of integration should be x values. So I look, my shape starts at 0 and ends at 2. So those are my limits. My radius needs to be in terms of x because I want an x integral. So if I look at what's controlling the radius, if I'm creating a circle like this as the cross section, the radius is found by going from the axis of revolution up to the function. Now, if I do that at different x values, you'll notice my radius is not staying the same. It can be longer or shorter depending on what x value. So that tells me that yes, my radius is a function in terms of x. And the curve that is controlling the outputs, the lengths, the y values, is y equals x squared. So therefore, I know my radius is being controlled by the function x squared. I go to my integral, I substitute x squared in, Remember to put another squared on it. And this is an integral you should be able to integrate. I'm going to leave that up to you to do. If you do the math correctly, you will get either 32 pi over 5 if you stick it out by hand, or you'll get approximately 20.106. So that's part A. Part B says, what if our axis is the y-axis? Well, the y-axis is, of course, vertical. If our axis of revolution is vertical, we need a dy type integral, an integral where y is the variable. And now I'm thinking about rotating it this way. So I'm going to go from my axis of revolution all the way to my shaded area. And you can see, there's a portion that's not shaded. In other words, there's a gap. So since we do have a gap from our axis to the shaded region, this will be a problem to do using washers. Our cross sections are going to look like donuts and have holes in the middle. So that means the formula that we're using is pi integral capital R squared minus little r squared dy. I need to get capital R and little r to be expressions in terms of y. Or they might be constant if we get lucky. To find capital R, I go from the axis of revolution to the furthest point on the shaded region. And notice what happens. No matter what y value I choose, capital R is always staying the same. So this length is 2. Capital R equals 2. Next, to find little r, I go from the axis of revolution to the bottom edge of the shape, the closest edge. And these are examples of what little r should be. Now they are changing in length, and they're changing according to this equation, because that's where those points are located. But notice we said we need our little r to be in terms of y. I need to take this equation, y equals x squared, and solve it for x. So I'm going to take the square root here and the square root of there. I'm going to remember to put my plus and minus signs on. And again, this branch of the function is where the x values are positive and the y values also turn out to be positive. So therefore, this is x equals square root of y. That's controlling little r. So little r will be square root of y. So I can now go in and substitute capital R and little r. For my limits of integration, they need to be y values. And the entire shaded region stays between this y value and this one. So we go from 0 to 4, and the entire shaded region is between those. So that's my limits. And then you really just have one more cleanup step where you can square 2 and obviously get 4. When you square the square root, you just get y dy, and again, this should be simple enough for you to integrate on your own. The correct answer for this one will be 8 pi, or the decimal equivalent. All right, now for the first time, we're going to do one where the axis of revolution is not just the x or the y axis. It's the same process, but the math is going to look a little bit different. So when my axis of revolution is x equals 2, I ask myself the same questions. First of all, is that a vertical or horizontal axis? And that one is, of course, vertical, which means I'm going to want a dy type integral. Now that I know that, I look and see if I have any gaps between the shaded region and the axis. And I don't. So that's nice. I have no gaps. So therefore, my cross sections will be disks. They'll be solid circles. So the basic integral formula I'm following is going to be the volume is equal to just regular pi r squared dy. Now I need to determine the value for little r, which is the radius. And because I have a dy integral, I need to get little r in terms of y. So when it's time to determine little r, what I want you to notice is take a point on the axis and go across the function to the edge in a couple different locations, and you can see that R is changing its length. The radius is different at different points. Now, we are no longer connecting to the x-axis or the y-axis, but we're connecting back to x equals 2. So you need to use what we learned when we were doing the area between two functions. So what we learned is, in that instance, if you want to find the area of a shaded region that's between two functions, we learned about integrating either the top function minus the bottom function, or integrating the right function minus the left function, depending on whether we were integrating with respect to x or respect to y. Now, in this instance, we are integrating with respect to y. So therefore, I need to calculate my little r by subtracting the rightmost function minus the leftmost function to get the value of the radius. So the rightmost function here is this x equals 2, or in other words, 2, minus my leftmost function is being created by y equals x squared. But remember, I don't want to just put x squared sitting here, because then when I go back to my integral, I'm going to have problems. I need it to be in terms of y. So I'm just going to take that equation that's causing me problems and switch it for the other variables. So I'm going to solve for x by taking the square root of both sides, remembering to put on my plus and minus. And this portion of this curve is the one where the x's, the inputs are positive and the outputs are positive, meaning it's this function in particular. Therefore, square root of y is my left function and goes here. So one more time. Anytime your axis of revolution is not the x or the y axis, you're going to need to either subtract the top function minus the bottom function, or the right function minus the left to get the radius. Once you make it past that, then you substitute what your r value is, squared dy. And like we said in the last example, the shaded region stays entirely between the y values of 0 and 4. So that's what I'm going to put here. Now, I'll take this one a little bit further here to make sure you handle this situation properly. There is no rule that says if you have a binomial squared, you can just distribute that squared into your integral. What you need to do instead is you need to remember squaring something means multiply it times itself. So I would want to rewrite this in this way. And you're going to use FOIL to multiply out and get 4 terms. When you do that, if you do it properly and simplifying as you go, you're going to have 2 times 2 is 4. Then you get minus 2 square roots of y. Then you get another minus 2 square roots of y, and then plus the square root of y times the square root of y, which is just y. Then I would combine my middle terms, and what I'm really looking to integrate is 4 minus 4 radical y plus y dy. And you won't have problems with this as long as you remember you're going to express the square root of y as y to the 1/2 power, do power rule down the whole integral, and if you do that properly, you should get 8 pi over 3, which is approximately 8.378. Let's look at another example. Y equals 1 plus the square root of x is one of our functions, and that's the curve. We have the line y equals 1, which is this horizontal line, and the vertical line x equals 4. And there's our shaded region that's bounded by those 3 functions. Now I want to go ahead and find the volume when we rotate around the x-axis, the y-axis, and y equals 3. So part A, if we're going to rotate around the x-axis is horizontal, and therefore we need to write an integral that will be in terms of x, or what I like to call a dx integral. And if we're rotating around the x-axis, is there a gap from the axis to the shape? And the answer is clearly yes. We've got this white space in there. So, because we do have gaps, we will be using washers. Our cross sections will look like donuts. So this information tells me that I need to use the volume formula that is going to subtract the two squared radiuses, and I want it to be a dx integral. I need to determine my capital R and my little r. To determine capital R, you go from your axis of revolution to the furthest point on the shaded area, and you do that in a couple of places. And I observe that it is in fact changing its value. It's shorter here and longer here. What's controlling where it stops is this function, which is y equals 1 plus square root of x. Do I want to just take 1 plus x and put it in for capital R? Absolutely, because I want a dx integral. So I can take that value as is. Now when it comes time to look for little r, I'm looking for the distance from the axis of revolution to the closest boundary of the shaded region. And if I do that in a couple of locations, you'll notice it's staying the same every time. Little r is always 1. So now I can substitute that into my integral. So I have pi integral of 1 plus radical x squared minus 1 squared dx. The x values, I look at the shape and they all stay between these two values on the x-axis, so that's from 0 to 4. Now again, I'm going to caution you when you're working through squaring this first term. Again, you cannot just square both parts. That's an illegal move. You instead need to write it as 1 plus radical x times 1 plus radical x. 1 squared is fortunately just going to be 1. And once you perform FOIL or distribution on your two binomials, you will get the integral 1 plus 2 square roots of x plus x, and then the minus 1. And then at this point, again, you can just use your power rule for integration, remembering that you're going to rewrite square root of x as x to the 1/2 power. And your answer will be either 56 pi over 3 if you tough it out with the values, or if you pick up a calculator, about 58.643. Now for part B. If my axis of revolution is the y-axis, that's vertical. So if it's vertical, I need a dy integral. Will there be gaps? So if I look at that axis and head to the shaded region, you can see there is a gap between axis of revolution and the shaded area. So since I have gaps, that means I'm going to be creating donuts that will have holes in the middle, or washers, when I revolve around this axis. So together that tells me that I'm going to want to integrate the two radiuses squared dy. Find capital R. You start at your axis of revolution and go furthest out on the shaded function, axis to furthest out, and hopefully you can see that capital R is staying the same this time. It's always 4 units long, so that's good news. Now, my little r is found by starting at the axis and going to the closest boundary of the shaded region, and you can see little r is definitely changing length. Therefore, my little r, I need to write an equation for it. These points are located on the function y equals 1 plus square root of x. However, I would not want to just put that in for my little r, because then when I go to my formula, I'm going to introduce an x in my dy integral. So this is a situation where I need to take this equation and solve it for x. So I'm going to subtract 1, and then I'm going to need to square both sides. So I get y minus 1 squared equals x. And that will be my little radius. Now I can substitute those values into the integral. So I'm going to integrate. Capital R is 4 squared minus little r is y minus 1 squared, which then needs to be squared, dy. My integral has entirely y's in it, so that's good. I need limits that are y values, and when I look at my shaded region, it stays entirely between these two y values. And make sure you're paying attention again, x-axis is down here. We're staying between the values 1 and 3. So that's going to be my limits. Now, in terms of simplifying that integral, 4 squared is 16 minus, I'm supposed to square something that's squared, so that's going to raise it to the 4th power. And if I were integrating this one, I would probably opt to split it into two integrals, where I do pi times the integral from 1 to 3 of 16 dy minus that constant pi, 1 to 3 of this portion. Reason being, the first integral is easy to evaluate. 16 is simply going to become 16y, which you have to evaluate from 1 to 3. And then the next integral, you can do a u substitution on. You can let u equal y minus 1. Therefore, du is dy. So this is really the integral of u to the 4th power, du. I'm going to integrate that, which becomes a pi in front, u to the 5th over 5. And then make sure that you put the y back in. You resubstitute that u was y minus 1 before putting your limits of integration back on. Because again, your limits of integration were y values, not u values. So in other words, this is what you are calculating. So now you should be able to use fundamental theorem of calculus to finish evaluating both of those. So for part B, your answer should be about 80.425. And the last one that I have set up for you is part C, which is to figure out when your axis of revolution is y equals 3. Y equals 3 is, here's 0, 1, 2, 3. Y equals 3 is this line right here. That's the one that I want to be rotating around. So as I look at this, first of all, for part C, that's a horizontal axis, which means I'm going to need my dx integral. And then the next thing, is there a gap between the shaded area and that axis? And yes, you can see white space here. So once again, because we have gaps, when we integrate, we will be having cross sections that are washers. So my correct volume integral format is going to be the one that subtracts capital R and little r. Capital R, you're going to start at the axis, go to the furthest out point on the shaded surface. Do that in a couple of locations, and you'll observe capital R is remaining constant, and it's always 2 units, because one of the boundaries of this shape was y equals 1. The axis is at y equals 3. These are always 2 units apart. So capital R is going to be 2. For little r, we want to take a point on the axis of revolution and go to the closest part of the shaded region. Those points are all falling on this function, which was y equals 1 plus square root of x. If I want to find out the distance from here to here, remember, when your axis of revolution is not the x or y axis, you need to fall back on the distance between two curves. I'm going to need to take the top function minus the bottom function. because I'm doing a dx integral. The top function, all these points are located on y equals 3. The bottom function, all these points are located on 1 plus square root of x. And notice this is in terms of x, so that's a perfectly fine value for little r. And we substitute here. The only thing we need in addition is what our limits of integration are. If we're looking at the x-axis, the entire shape stays between 0 and 4. So this is what we're integrating this time. This integral does clean up a little bit. I'm going to go ahead and distribute this subtraction sign into both of these terms. Then I can do 3 take away 1, which is going to be 2 minus the square root of x squared dx. And again, we've seen how to handle this situation. Again, integrating 4 isn't going to be a problem. Here with the second term, you're going to remember that squaring something means multiply it times itself. Once you finish integrating that by hand, you will get the exact value of 40 pi over 3, which is the same as the decimal equivalent, 41.888. So hopefully that's enough examples to get you confident in the method that we use for finding the volume of solids of revolution.